Hello class. In this lesson, you will learn to convert between exponential logarithmic form and also evaluate logarithmic expressions using exponents or the change of base formula. Let's begin by going over what a logarithm is compared to an exponential function. Now, the inverse of an exponential function is called the logarithmic function with base a, and a logarithm, or log, short, which we use log for short, is another way of writing an exponent. So for example, if I have the log of a base b of a and it's equal to x, this log base b of a equal to x, as that's the way it's read, is equivalent to getting this base b, raising it to the power of x, and it's going to equal to this value of a. So what we're essentially doing is just simply writing this exponential equation using this notation of log. So they're again equivalent to each other. And we are figuring out essentially this value of x here, the log base b of a is equal to x, means that if I get this value of b, what power do I have to raise it to in order to get this value of a? That's what a logarithm does. So for example, before we go into an example, let's discuss again the common logarithm. A common logarithm is a logarithm with a base 10 and is normally written without the base. So if I have the log base 10 of a, that's normally written simply as the log of a. We don't write the 10. It's understood to be 10 when it's omitted. So let's look at some examples of how to write these logs into an exponential form. So let's say we have this logarithmic equation. We want to convert it in exponential form. So here, I would start by identifying the base, which is 7. I would raise it to the power of 2, and that will equal to 49. So the log base 7 of 49 equals to 2 is the equivalency of this. 7 to the second power is equal to 49. And look, it fits in again. The equation is true. If I raise 7 to the second power, it does in fact equal to 49. Look at this example. If I have the log base 4 of 1 over 64, that's equal to negative 3. So the base of 4 raised to the third power, negative third power, is equal to 1 over 64. And there is your solution. This is the equation in exponential form. For the third example here, in exponential form, the log base 8 of 1 is equal to 0, means that if I get 8, raise it to the 0 power, that's going to equal to 1. So this is the exponential form. Now, to go backwards and to convert from a exponential form to a logarithm, I do the exact same thing, just simply work backwards. So right here, I need to identify the base, which is 10. So if I get the log of base 10, which is the common log, of this value here of 1 over 100, that's going to equal to the exponent of negative 2. And this is normally written like this because it's the common base. We only write the log of 1 over 100. You might want to put parentheses, not required, of it equals negative 2. Since our base is 10, we don't have to write it. It's understood to be 10 when we just omit it. So let's look at another example here. Since our base is 5, we're going to take the log base 5 of 1 equals to 0. So the base of 1 equals to 0. And this last one here, the log base of 81, base 81 of 9 is equal to 1/2. And there's your answer. So to convert from exponential form to logarithmic form, again, just simply requires to identify the base. And in this situation, the value that it equals to is the exponent right here of that base. Now, because of this, we can use this technique to evaluate functions. When evaluating these logs, remember that a logarithm is an exponent. We can rewrite this as an exponent. What this means is that the log base b of x equals to the exponent that b must be raised to in order to obtain this value of x. So the value of this, to identify what this equals to, I'm basically looking for, okay, what power do I have to raise this number to, this b, in order to equal to this value of x? So for example, the log base 2 of 8 is equal to 3. I know that this is going to be the answer of 3 because if I get this value of 2, raise it to the power of 3, that's going to equal to the answer 8. 2 times 2 times 2 is in fact equal to 8. So I know that the answer has to be 3. And using that train of thought, using again this conversion, I can figure out the value of a log. So for example, this one right here, what is the log base 4 of 64 equal to? Well, here I'm essentially trying to evaluate the following expression. So if I get 4 and raise it to some power, I should get this value of 64. So the idea is to basically figure out how many times can I multiply 4 by itself until I get the value of 64. Well, in this situation, that would only have to be 3 times. 4 times 4 is 16, and 16 times 1 more 4 is equal to 64. So I would have to multiply the number 4 3 times. In other words, raise 4 to the 3rd power, and that's going to equal to 64. So this is the value of this logarithm. This log base 4 of 64 is equal to 3. So using this definition, I can then figure out this value. So for like this example, 6 to what power, I'll write an x instead of a question mark, is going to equal to 36. So I'm again asking essentially this question, how many times do I multiply 6 to get 36? Well, that's 2 times. 6 times 6 is equal to 36, which means 6 to the 2nd power is equal to 36. So this is the value of our log. So the log base 6 of 36 is equal to 2. So this is our answer. Now this is a common log. So here our base is 10. So 10 is going to be raised to some power to equal to 1 over 10. So for this example, it's probably a good idea to understand again our powers. If I have x 10 to the 0 power, we should know that's equal to 1. If I have 10 to the 1st power, that's equal to 10. 10 to the 2nd power will be 10 times 10, which is 100, and then so on, 10 to the 3rd, which would be 1,000. Now we want 1 over 10, not 10. So as you see right here, 10 to the 1st will give me 10. So if this was a 1, this would be equal to 10, but I want 1 over 10. Well, I get the reciprocal of that when I raise our 10 to the negative power. Since 10 to the 1st power is equal to 10, 10 to the negative 1 is not negative 10, but 1 over 10. Just like 10 to the negative 2 power would be 1 over 100. Simply the reciprocal of this value right there, and then so on. The pattern repeats. So here, our exponent would have to be a negative 1. 10 to the negative 1 power is equal to 1 over 10. So that means that the value of this log is negative 1. This is the answer that I'm looking for. Now let's look at this one. In this situation, 16 is our base, and we want to raise 16 to some power to equal to 4. Well, the only way to get 16 to equal to 4 is if I take the square root of 16. The square root of 16 is equal to 4. Now in terms of exponents, the square root of 16 is the equivalency of raising it to the 1/2 power. So here, our exponent would have to be 1/2. So this is the value of this log. The log base 16 of 4 is equal to 1/2. And that's usually what happens when I have a base that's bigger than the value. That means that this exponent has to be some type of fraction. If I have the reciprocal, if it was like 1 over 4, then it would be not just 1/2, but it will be the fraction of that. It will be the negative of that. And this last one here, I have the log base 5 of 1, and I want to know what is this going to equal to. So if I get the base of 5, raise it to some power, I need it to equal to 1. Well, that one you should know that is going to be 0. The only way to get any number to equal to 1 using exponents is if I have that exponent be a 0. 5 to the 0 is 1, 6 to the 0 is 1, anything to the 0 power is equal to 1. So here my answer would be 0. This is what we're looking for. So here we have 2, the log base 2 of 1 over 8. So that means 2 to the x power is equal to 1 over 8. And again, just like 10, if I have 2 to the 0 power, I know that's going to equal to 1. 2 to the first power is equal to 2. 2 to the second power is equal to 4. 2 to the third power is equal to 8, and then so on. But since I want 1 over 8, the reciprocal of this, that means that my value would have to be 2 to the negative third power. That's equal to the reciprocal of 8. So here, 2 to the negative third is equal to 1 over 8. So our answer here is negative 3. Now, this again is when we use again these integers as our basis. Now, what happens when we use again the natural base in these logs? So the natural logarithmic function is going to use the base e, and this is referred to as the natural logarithm. And it's written in the following form. So the log base e of a is written using the letters ln, and that's the way we read it. We read it as ln of x, or in this case it's going to be a, or simply the natural log of a. Now, the natural logarithmic function and the natural exponential function are inverse functions of each other. So every logarithmic function can be written as an equivalent exponential form, and every natural exponential equation can be written as an equivalent logarithmic form. So for example, here the equation ln of x is equal to 5 can be written as an exponential form as e to the 5th power is equal to x, because this is the log base e of x is equal to 5. So I can write it like this. So for example, this is the equation of the log base e of x is equal to negative 2. So therefore, I can write this as e to the negative 2 is equal to x. And of course, I can also go backwards and write this backwards. This, because our base is e, I can write this as the log base e of 3 is equal to x. But since this has the base e, I rewrite this as simply using the letters ln. So ln of 3 is equal to x. That's the standard way of writing that log with base e. So like on this example, this would be the ln of x is equal to 0.5. So this is how I convert this exponential equation into a logarithm using the natural log. Now, to evaluate logarithms, you'll notice that on your calculator, most calculators, again, even on our Desmos calculators, there is the logarithm button on the devices. So for example, let's get our log here. Let me get my Desmos calculator here. Here I want to get the log So that's under functions, and you'll notice that my log is on the right side of the screen. I have the log of the number 9. That's equal to the decimal 0.54. So to evaluate a logarithm, we have to use a calculator in some situations. Like right here, I cannot evaluate this using my exponents, because here my base of 10 to the power of x is equal to 9 would not be done, because 10 to the first, so 0 power is equal to 1, but 10 to the first power is 10, 10 to the second is equal to 100, and then so on. 10 to the third would equal to 1,000. So here the only way to calculate this log is if I use again a calculator, because this value for x, this exponent I'm raising 10 to, is going to be some irrational number, and specifically this irrational number is close to 0.954. So 0.954 would be the estimated value that we would have to raise 10 in order to get it close to 9. And again, we can check that out. So look, if we get 10 and we raise it to this 0.0954, I'm sorry, it's 0.954, not 0.954. Notice it gets really close to 10. The more decimal points I use, the more accurate it becomes. So if I put the next decimal point, the next value, which is 24, notice that the number gets closer again. My answer gets closer and closer to 9. So here we would have to use our calculator in order to estimate this value, because using exponents is not going to work. And with natural logs, you definitely need to use a calculator in order to measure and evaluate this function, because here, since this is the log base e of 25, and we want to know what is this going to equal to, that means I have to get this e, raise it to some power in order to get this to 25, and that's going to be difficult because e is the irrational number of 2.71. And to get this to 25, well, again, you won't be able to guess using whole numbers. It's going to be some type of, again, decimal value. So we'll approximate that decimal value by using our calculator. So here, let me clear this. Under functions, I see the ln button, again, the natural log key on the right side of the screen, and 25 estimates to 3.219. So this is the estimated value. Now, most calculators only have those two keys. They only have the common log, and they only have the base 10 or the natural log base e key. And while those are the most frequently used logarithms, you may occasionally need to evaluate logs with other bases that does not work well with exponents. So to do this, you want to use the following change of base formulas. So let's say I have the log base b of a. The change of base formula then dictates that if I get the log of the a and divide it by the log of the base b, again using the common log base 10 of a and log base 10 of b, and divide those two things, that will equal to this value here. Or if I don't have the common log, I can use the natural log. I have the natural log of a divided by the natural log of b will also give me again the log of this base b of a. And this is going to be perfect again for examples where the exponent rule doesn't work out. So for example, look, like for this one, this I want to get 5, raise it to some power x, and make it equal to 34. Well, there's no whole number that I can raise 5 to in order to get 34. 5 to the first is 5, 5 to the second is 25, 5 to the third is 125. So obviously this number, this exponent, has to be a number between 2 and 3 because 34 is between 25 and 125. So there's no way of calculating it using whole numbers, and it has to be a decimal. Well, the way we're going to figure out that decimal is then, since our calculator only has the common log or the natural log, I can evaluate this, since this is not going to work, I can evaluate this by using the change of base. So if I get the log of 34 and I divide it by the log of 5, the common log, of course, the common log of 34, and I divide it by the common log of 5, that will equal to the same thing as this up there. So let's use our calculator. So the log of 34 and divide that by the log of 5 is approximately 2.191. So this is the value of this, of the log base 5 of 34. So 2.191. So that's how we use the change of base to evaluate these logarithms where the exponents, the exponent or converting into exponent does not work. So like right here again, we're trying to figure this out. We're trying to figure out this exponential equation. But again, using our powers and multiplying 5 by itself so many times doesn't work because we cannot make it equal to 34 because it's going to be a decimal. And again, we can verify this by getting 5 and raising it to, again, 2.191. See how it gets very close? 33.99, 0509 86, and look, that gets really close to, actually it equals to 34.00001. So you see, only that number will make 5 equal to 34, raising 5 to this power. And that will be a tough number to guess and try to figure out without our calculator. So, and because our calculator only has those two keys, the natural log and the log, we would have to use this change of base. And it also works if, like I said, if I use the natural log. So look, if I use the natural log of 34, oh, I'm sorry, let me hit enter. If I use the natural log of 34 and I divide it by the natural log of 5, I get the exact same answer. So it doesn't matter which of the two logs you use. So either the common log or the natural log, as long as, again, you put 34 on top and 5 on the bottom, you get the same answer. So for number 20, in order to evaluate this, I would get the log, using the change of base, I would get the common log of 1/3 divided by the common log of 6, or the natural log of 1/3 divided by the natural log of 3. So plug in either of those into your calculator, and that's how you evaluate this. Which in this one would equal to negative 0.613. So this would be your value. And for this one, we can use again either the common log of 100 divided by the common log of 4, or the natural log of 100 divided by, put too many zeros on that one, divided by the natural log of 4. The one thing you cannot do this. This will not be the common log of 100 divided by the natural log of 4. That will not work. Or getting the natural log of 4 and dividing by the common log, the common log of 4 and the common log of 100, okay? If you flip these numbers and put these in the wrong order, the 100 on the bottom and the 4 on the top, whether it's a common or the natural log, you're going to get the wrong answer. The 100 needs to go on top and the 4 needs to go in the denominator. And you cannot mix a common log with a natural log. That's going to give you the wrong answer as well. So do not make these mistakes. And that gives us an answer of approximately 3.322. On your assignment, make sure that you estimate all your answers to the third decimal point and there's thousands as indicated in the instructions, in the directions. And then finally, even on ones that you can possibly, where you can even use the power rule, like on this one, we can use the power rule. 3 to the power of x is equal to 27. And this would be 3 times 3 times 3, which is 9 times 3, which is 27. So here, 3 to the third power is equal to 27. So that's the answer here. The log base 3 of 27 is equal to 3. We can still use the change of base formula. So if I use the common log of 27 and I divide it by the common log of 3, this is going to equal to 3. When I use the natural log of 27 and divide it by the natural log of 3, this is also equal to 3. So in those situations, I could even use again my change of base to get the same value as if I would use the exponential property and convert this into exponents and then just simply multiply the number 3 out until I get 27, which in this case would be to the third power. So you see, let's do that one. The natural log of 27 divided by the natural log of 3, you see, equals to 3. So even in those type of problems, you can even use this change of base. So if you cannot figure out using exponents, you can just go straight into the change of base formula to evaluate logarithms using, again, the common log or the natural log. Well, there you go. That concludes, again, the end of the examples. If you do have any questions, please send me a message on Remind or through email. And again, I appreciate you watching, and I hope you have a great day.